Hi everyone. So in this video, I would like to discuss today's LeetCode daily problem. So the problem title is find the count of good integers. Okay. So basically, what does the problem states that we need to find count of good integers, and the definition of good integers is that if you read the definition, if its digit can be rearranged to form k palindromic integer, and the definition of k palindromic integer is x is a palindrome and x is divisible by k. Okay, so basically what does it say? We need to find count of good integers. Okay, and what is a good integer? A good integer is any k palindromic integer, or which can be, so basically any integer which can be rearranged, which can be basically rearranged to form k palindromic integer. And what is a k palindromic integer? We have if x is our integer, so x should be a palindrome and x should be also divisible by k. So this is a overall problem statement. Okay, and we need to count all of this good integers. Okay, now if you see the constraints here, so constraints here are basically n less than equal to 10 and k less than equal to 9, I think, right? So we have these constraints. So very first thought which comes in mind is like, why not just generate all the permutations, or you can say all the numbers, right? We have just 10 digits, right? So we can think of that, right? 10 digits are not very large, so we can basically store our number in form of strings, and we can generate all those 10 digits integers, right? And then we can just check whether it's divisible by k or not, right? And then also we can check that if it's a palindrome or not, right? And then we can count every number. What we can do is like we can generate those numbers, and then we can check whether it's a palindrome or not, or and if it's a palindrome, then we can check whether it's divisible by k or not, right? Now once then this becomes a k palindromic, right? And then when it becomes a k palindromic, then we can rearrange these numbers as well, right? So that is the very first thought which comes, right, to generate all the numbers. But the thing is, if just in the worst case, we will need to generate a 10 digit number, right? So just imagine 10 boxes, and we need to fill these boxes with digits from 0 to 9, right? So each boxes have 10 options, right? So that becomes like 10 to the power 10 combinations, like overall in the worst case, right? So the order, if the time complexity, if I have to say, right, so time complexity is of the order this, like in the worst case scenario, and this will definitely result in TLE, right? So we need to see we need to think of a smarter approach here, right? And this intuitions come from the fact that we need to find some palindromes, right? And any number which can be rearranged to a palindrome is going to be a good integer, right? So if I say a number like 110 22, right? So okay, right? So this can be rearranged to form a palindrome, right? So we can do something like 12021, right? So why not we just try to count all the palindromes first? And in order to count palindromes first, we don't need to go 10 to the power 10, because we can just split our palindrome into two lengths of n by 2 and n by 2, right? And then we just form our palindrome of n by 2 numbers, only the first half. and the next half we generate by using the first half. Now once we have that palindrome, we can check whether its palindrome is divisible by k or not, right? So this seems of a fairly good optimization, because now we don't have to go and, you know, now we just have at max 5 boxes, and which is like 10 to the power 5, right? So at in the worst case we'd be kind of generating 10 to the power 5 numbers, right? Using recursion we can do this, right? So this is fine, just can work, right? And then we'll be checking, and to check it's a constant operation, right? Because we will be making it in form of string, and palindrome will not be having more than 10 length of 10, right? So that will be an O of 1 operation, right? Now, but now there is actually basically, to generate, what we can do, we can just write a generate function which will be kind of taking our index and the string that we are generating, so, and n. What we'll do, if I equals to n by 2, then we can just push this, and this will be like our first half, right? So we can just push this in our first half. I can show you the code for actually that. So let's try to go and check the code for this, right? So this is the generate function, which is just generating half part, right? So my half part vector is kind of so my half part vector is kind of storing only the half parts of this string, right? Now you can see I'm not generating all those string, because here there is a note here in the question that any integer must not have any leading zeros, okay? Neither before nor after arrangements, okay? Now the thing is, that's why I have put this condition that the recursion will not work in this case if I'm at position 0 and my digit is 0, right? So now I'm able to generate the valid half part of these strings, right? And then what I'm doing, the first half is this, and the second half is also the same, but the second half will be reversed. In the original palindrome string, it will be reversed. Now there comes a case when we have n, whether it's even or it's odd, right? So if it's even, then we don't need to do this, right? So if even, let's say n is equal to 4, right? So we have like, we can definitely in equal parts we can split this string of 2 and 2 length, right? But if n equals to 5, we need to have 2 and 2, and then there will be something in the middle, right? So that's why there is a case, I think this is fairly simple to observe, that yeah, we need to put something in between for n equals to odd, right? And I'm just storing it in palindrome list. So basically for in odd cases we can have at most like 10 different palindromes for one half part of the string, right? And in case of even, we'll just have one string for each half part, right? Now after this comes the case of calculation, right? So now here what we had thought ki we could rearrange these numbers and we can find the count using combinatorics, right? So now the numbers we have, right? So we can just check the numbers. So after generating the numbers, we can just use the stall STL to convert the string into long, and then we can check whether this number is, you know, divisible by that or not, right? So that's what I have done here. Now the thing is like, how do we count the numbers? How do we count distinct numbers specifically, right? Or you can say the unique numbers. So let's say if you have a permutation like 5 1 5 5 like this, let's say this is the number, right? So how many different numbers can we, you know, generate from this? Good integers, like in terms of question, right? So we can have 5 1 5 5 5 as well, right? We can have 551, which is already there. So let's try to do this like this: 55515, right? So we can also have 55551 as well, right? Similarly, we can do this in the back side as well. Like we can shift this by left, so 51555, right? And then we can also do 15555, right? So this is like the total unique numbers that we can generate. So this is like coming out to be 5, right? So can we generate anything other than this? If we have this palindrome, right, and this is like k palindrome, that is, it is divisible by k as well, right? So the number of good integers, how many good integers that we can generate from this k palindrome is 5, right? And this is basically the math about this is that given a string, right, given a string, if you have, let's say, similar characters, right, 5 1 2 2 3 4 6 5, okay, I'm not considering a palindrome as of now, right? This is just a basic question which can help with this calculation, is that how many unique numbers would be there, like how many unique strings we can permute, right? Right. So the here, by unique, what do I mean is, like, I can see there are total of 5 numbers. Like if I consider this example, there are total 5 numbers, right? But if I do 5 factorial here, right, so 5 factorial will not give me all the unique permutations. Here we need to find all the unique permutations, right? So this is basically how we can do is 5 factorial is the total number of permutation, and we know that there will be some sort of repeated permutations as well, and these permutation will be what? It will be the frequency of each number. So basically any permutation which is kind of having a clubbed permutation of different numbers, right? Like if we have 1 1 1 1 clubbed, so these permutation we need to kind of divide from our total permutation, and that's why we need to divide the frequency of each number factorial, right? That's how we get the number of unique permutation. Okay, so that's why then you go and you actually write the function of so you write a factorial function. This is fairly easy, and then you write basically how can you write the total number of unique permutation. So that will be your total permutation, that will be s dot size, the string size, and then you can calculate the denominator, which will be like factorial of this specific character frequency multiplied in the denominator, and then you just divide it. That is the total unique permutation. Now the last part of the question is, how do you erase or you can remove those counts, because this will be having, even let's say if we have a string which has like zeros, 2 0 0 1 0 0 2, right? Now this is a palindrome. Let's say we have got this and we are trying to count number of unique permutation for this, right? So number of unique permutation as of our calculation is fine, but it says that there should be no leading zeros. Now do you guys agree that there will be some permutation where we'll have leading zeros, right? We'll have leading zero as of here, right? Also I think, yeah. So how do we kind of remove those permutation? That is the question, right? So we can again use the same fact that we use over here to remove those permutation. So what I did, basically I fixated this position with 0, and then I did the number of unique permutation for these many places. Okay, now this will guarantee that all of these numbers, so all of this set is having leading 0, right? And we can subtract that from our total number, right? So basically what I meant to say, let's try to rephrase again. uh, Very first time when I calculated this total, right? So this is what it is doing. It is giving me the unique permutation of this, all the unique permutation of this string, right? All the unique permutation of this string, right? So which will be, if I see 7 factorial divided by the frequency of 2, which will be 2 factorial, and then the frequency of 1, which is 1 factorial, and then the frequency of 0, which is 4 factorial. Now in all of these permutation will definitely have zeros as leading, right? So why can't I say, so now what I'm doing, I'm taking one of the 0, I'm just fixating it over here, and then I'm trying to count all the unique permutation, of 6 digits. Okay, so 6 digits, right? So if I do the same thing here, now what I'll do, I'll have 6, now I have 6 places to fill, so 6 factorial, and I have 3 zeros, 1 and 2 ones, right? Now can I say like this will be the total number of strings having leading zeros, right? So that's how we can minus those frequencies. So that's what I've done. So if frequency of 0 is greater than 0, then we just minus it, right? And if 0 is not there, then that's the total number of answer that we want to calculate, right? And this is exactly what I'm doing. I'm just basically subtracting those, removing k palindrome string with leading zeros. Okay. Now there could still be a case. This is where I was missing. I don't know like how many of you while solving whether understood this or not. The palindrome that we are generating, right? So if you see our generate function, do you agree that this can even generate first half? We are talking about we were generating only the first half. That this can generate some sort of first half like this. So one generation could produce a string like this, as well as it can produce a string like this as well, right? And now when we go and try to find the permutation for these two strings differently, then we will be doubling, or you can say we'll be adding more to our answer, like we'll be doing some double counting, right? So this is the case of double counting. So this basically I understood after seeing a few description or what discussion, right? Because when this is fairly there are a lot of problems, or you can say sub problems to solve in this question, so you'll miss out on few things when concentrating on other things, right? So this is what we were doing as a double counting, right? So to avoid that, what we can do, we can just create a visited set. Okay, now in the visited set, what I do, I just count only if I get a unique palindrome, and that's how basically this question is getting solved, right? So this was I think most of a maths question than DSA. So yeah, thank you guys.